The tilt of our planet's rotational axis is about 23 degrees currently, and it's that tilt that gives us our overall seasonal pattern. It turns out that if we didn't have our moon, or if we had a moon but it was just smaller than our current moon, that interactions with the other planets in the solar system would cause Earth's rotational axis to vary by many tens of degrees on timescales of millions of years. This would have profound impact on the overall climate of the Earth. And while the Earth, with such a wildly changing tilt, might still have been habitable, it would certainly have been an entirely different climate and a different Earth than we have today. And so in this way, the formation of our moon and the formation of our moon of just the mass of our moon has had a very important impact on the evolution of the Earth's spin state, and with it, the evolution of our long-term climate. There's a fundamental connection between our studies of the origin of the moon and the physical samples that were brought back by the Apollo mission, the actual rocks from the moon. When those rocks were first studied, we learned several very significant things. One, we learned that compositionally, those rocks are extraordinarily similar to the upper layers of the Earth. If you look at an element like oxygen, its distribution of different isotopes of oxygen is essentially identical in the moon and the Earth, whereas it's very different in meteorites from Mars or the asteroid belt. Another clue, another constraint we learned from the Apollo samples is that the moon rocks appeared very dry compared to Earth rocks, almost as if they had been heated to a high temperature and that they had lost the elements that tend to vaporize easily upon heating. And that suggested to us that the process that formed the moon must have been a high-energy event. So we think the moon formed when the Earth was struck by a very large object as the Earth was forming. So this would have been a separately formed planet that was vying for dominance in the inner solar system along with the Earth and other growing planets. But it collided with the Earth and ultimately was absorbed by the Earth and gave birth to our moon. So in terms of the impactor, which we often call Theia, we think that based on its mass, that it would have been as big as the planet Mars. Before it collided with the Earth, it would have had an iron core and a silicate mantle, like the Earth, and it would have had about 10% of the mass of the Earth. We think initially the inner solar system had maybe 20 small planets, and it was through collisions between these planets that we eventually ended up with our final 4 terrestrial planets. Now, the last of these big collisions on the Earth was the one we think formed the moon. The reason that we focus on a Mars-size impactor is that that is the impactor size that if you hit the Earth with a Mars-size impactor at an off-center angle at the expected speed, you will start the Earth spinning with about a 5-hour day. Now, that's a very rapid spin rate, but it turns out that is what is needed to agree with our current 24-hour day with the moon at its current distance. The moon is moving away from the Earth, so we know when the moon first formed it was much closer to the Earth and the Earth was spinning much faster. So the idea that the moon formed by this giant collision with the Earth was first proposed in the mid-70s, and yet we couldn't test the idea initially. For smaller scale collisions, you can perform experiments in the laboratory, but you can't perform an experiment of what happens when 2 planets collide in any laboratory setting. To do this, you need to build a computational model to simulate the planets and their response to the collision. We can use our computer simulations as, in essence, a virtual laboratory to test how the outcome depends on things like the size of the impactor, the impact speed and angle, and use the overall results to assess the likelihood of forming a moon like ours. So we're simulating this final large collision with the Earth. From the perspective of someone on the Earth at the time, what you would have seen is an enormous object approaching the Earth, many, many, many times larger than the full moon in the sky. It would have hit the Earth at an oblique angle. On a time scale of a few hours, an enormous shock wave from the impact would have propagated around the entire surface of the Earth. The vaporized rock from the initial impact point would have been ejected out, and it would have flowed around the entire Earth. And the Earth would find itself enveloped by a thick atmosphere, but not like an atmosphere we know today. This would have been an atmosphere of vaporized rock with a temperature of more than 5,000 degrees. The momentum, the force of this collision, is enough to start the Earth rotating very rapidly. And so only hours after this impact, the Earth has a rapid rotation rate. Now we think on a much longer time scale of about 100 years, that disk will cool, the vapor will condense, and out of that disk, through collisions within the disk, the moon would have grown and accumulated. So although we think we have a good idea about how the moon formed, the exact details of this event are still being debated, and this is in large part a testament to how those samples that were returned decades ago are still driving active science debate as ongoing analysis provides us with more clues from those samples on how the Earth-Moon system formed.